Okay, so let's go for the next example, that is linear regression. Now here again we have given the title as linear regression, and the data set that we have is the weather. Now this data set belongs to the data of weather during the Second World War, when the army wanted to bomb, right? Now this linear regression with weather data set during the Second World War air bombing operation, and this data set contains information on weather conditions recorded on each day at various weather stations around the world. Information includes precipitation, snowfall, temperature, wind speed, and whether the day included thunderstorm or other poor weather conditions. So our task is to predict the maximum temperature, taking input feature as the minimum temperature, right? So we are going to import all the required libraries like pandas, then numpy, matplotlib, then seaborn as a seaborn instance, whatever name you want to give. There is no restriction, but the library should be correct and the spelling should be correct. Then from sklearn dot model selection, this is again important because we have to calculate that whether the model is right or not. So that is why we are importing the sklearn, and we are also importing the train test split, because we have to train the data. First we have to train the data and then we have to test it there. So in what ratio we are going to train and test, that will come with the help of this import of this particular sub libraries. Then sklearn model import linear regression, because that is what our objective, to calculate linear regression. And then of course the sklearn for metrics, for measuring it. So these are the important libraries which we are going to use in this particular exercise. Now the data set we have is again like weather.csv. Now this is the data set which will be available to you, and then this is the data frame which is defined like this. So this is the complete path, of course, but we are only concerned about the data set. So whatever is your path, wherever this particular file is residing, you have to give that path, right? So you can see df is equal to pd dot read, because this is a csv file, so read underscore csv, and then the path and the file, right? So once you run it again, now let's first clear it. So restart and clear all the whatever has been there. So if we clear all this, you'll see that all these process numbers will go off, and we can run one by one. There's no action on this. This again can be run like this, and there will be some time because we are importing all the libraries, so it may take some time. Then we are going to run this because we need the data to be available, so we run that also. You get again this kind of warning. Now it is very important to do the data exploration, because we have got the data file, but we don't know what exactly is it. So one thing is that you can open it in Excel and see the data. That is, of course, is always required, and you can see that. But we can also see it here in this particular program. So when you are writing a Python code, you can, after importing that data file, you can see that what is the shape like. Shape means let me run this. So once we run it, you can see that it has 1,19,040 rows. These are the rows and these are the number of columns. So 31 columns are there and 1,19,040 rows are there. So this gives you that summary of that data. Then we are going to see the top 5 rows of the data. So the df.head means that we are only the head part, not the entire data. Entire data is going to be 1,19,000 rows. So that we are not going to see. We only want to check 5 rows only. So for that, df.head, and then run on. So you get this first top 0, 1, 2, 3, 4, and these are the, and with all those columns that are there, all these columns are going to be there in this, right? So this is how you are going to get your summary of the data, and here says the 5 rows plus 31 columns, right? Then we can also check with the describe. Now if we run it, let's see what comes. So when we run it, you'll see that it gives you all the statistical summary, that is count, mean, standard deviation, minimum, and then 25 percentile, 50 percentile, 75 percentile, etc., and then the maximum also. Now we have here 8 rows and 24 columns, and then all these things are coming again from the same data file that we have imported. right? And this you can see here also, like the one. You can also see here some nan. Nan means that it is not a number. That means this is something like you must have heard about the null values. This is something like that. So it is not 0, it is nothing else, but then it is there. So that means we have to take care of that. Whether it is required to be taken care of here in this particular exercise or not, but whenever it is required, we need to handle this. And we will come across with that situation. Now, and finally, let's plot our data points in a 2D graph to eyeball our data set and see if we can manually find any relationship between the data using the below script. We have taken minimum temperature and maximum temperature for doing our analysis. Below is a 2D graph between minimum temperature and maximum temperature. So again we can run it. Again it is remarked, so nothing will happen. But here this is the code that we have written to plot a graph between minimum temperature and maximum temperature. X axis will show minimum temperature and y axis will show maximum temperature. And style is 0. Now plot is title will come like minimum temperature versus maximum temperature, that is the title. Then x-axis it will be minimum temperature, y label is equal to maximum temperature, and when we click on this plot show, you will get the graph. So now you are going to get this graph, minimum temperature versus maximum temperature, all these data points are appearing here. Maximum temperature is coming here, minimum temperature is coming here on the x-axis. And these are the various points on blocks in which the data point has been covered, right? So this is how you get the scatter plot for this. Now let's check the average maximum temperature, and once we plot it, we can observe 25 and 35. When we observe it, that the average maximum temperature is between nearly 25 and 35. So average temperature you will find is between 25 and 35. So again here you can see that we have written a code like plt.figure. Fixed size is 10.10, 10 means that this is the lengthwise, right? Or maybe in this case you can say horizontally, and 5 is the height of that. So this is the total size of the graph that you are going to get. Then plt tight layout and seaborn instance dist plot. The name of the plot is going to be dist plot. Now these things again come with practice. You will see that it is difficult to say, but then once you see once or twice, then you will get to know about that what is the type of graph that we should have. And the data frame is maximum temperature that we are going to get here, right? So we can run it and we can see that you are going to get a kind of this graph here. This is a distributed plot because it is all getting distributed, and this is that size of the graph, that 10 by 5. So this is how you can understand that how the graph will appear, and this is based on this kind of a code that is written here, right? Now this gives you a very clear indication as to how the temperature has varied over time, and this is between 20 and 40 you are seeing the maximum temperature, right? So this is how, this representation, that is why the visualization is very, very helpful. Just by looking at the graph you can say that yes, how the temperature varied during different timings or different phases, right? Now here you can say that our next step is to divide the data into attributes and labels. Attributes are the independent variable, while the labels are dependent variables whose values are to be predicted, right? And in our data set we only have 2 columns. We want to predict the maximum temperature depending upon the minimum temperature recorded. Therefore our attribute set will consist of the minimum temperature column, which is stored in the x variable, and the label will be in a maximum temperature column, which is stored in y variable. So again this is just for our understanding, so nothing will happen as such, but we must understand it. Now here on x, x is again the variable where we are going to define the maximum temperature values, reshape -1 to 1, and then y again df maximum temperature, minimum values, reshape -1 to 1. So once we run it, you will get the it is just a kind of a assignment. So you are assigning to x and y what are the different values they are there. Now next we split 80% of the data to the training set. Now we are going to, because once we have to do this kind of analysis, then we have to first assign, and then we have to train the data. Now training of data is very important, and how to decide about the ratio in which the data is to be trained, that is something which again comes with practice and experience, and of course knowledge of your own data. So we split 80% of the data for the training set, while 20% of the data you can see for the testing set using below code. Now the test size variable is where we actually specify the preparation of the test data. Now this is not fixed. This 80% and 20% is not fixed. You can change it and see the result, because it is all for us to understand it. So whatever we think that this is the ratio, maybe if you are not satisfied, you can change it to 70-30, or maybe you can change to 90-10, or whatever, 65-35. So whatever ratio that you think will be fitting the best, that we can decide, and that accordingly we can train and test the data. So here you can see the next code that we have written is x train. That means first we are training this x variable where we had transferred the data earlier, and then the remaining are going to be in the test from the x variables. Similarly y train and y test, and then this is the way we are going to write for the division of the data set, that is train test split. How you are going to split it from x and y? Test size is equal to 0.2. Now 0.2 means that 20% we are keeping for the testing part. That is why it is test size. Test size is equal to 0.2. So the balance will go for the training part. So this is how the code is written. And then the random set means is equal to 0. This means that there is no iteration. Now this also you can decide that how many iteration that you want, because that again comes with your experience or understanding of your data set, that how many types you want to calculate, so that our result will come as accurate as possible. So here we are taking no iteration, so because 0, and this is what so again if we run it, nothing will happen, but then data will definitely be divided in this ratio. So once we run it, you will see that this says process is complete. And after splitting the data into training and testing sets, finally the time is to train our algorithm. For that we need to import linear regression class, instantiate it, and call the fit method along with our training data set, right? So this again we can run, no effect will be there as such. But here regressor is equal to linear regression. Now linear regression, if you remember, we imported that at the top, and that is going to be fit into this kind of a x train and y train, the data that we have trained on. So here we have seen like x test, y test, x test, x train, x test, y train, y test. So this is the data that we have trained here, and this is where we are going to check the regressor, where we are fitting on this data our regression, right? So training the algorithm is done, and then the regressor has been fitted. So as we have discussed that the linear regression model basically finds the best value for the intercept and slope, which results in a line that best fits the data. To see the value of the intercept and slope calculated by the linear regression algorithm for our data set, execute the following code. So we are going to execute this code. This is again for our understanding remark, right? Here you can see that to retrieve the intercept. Now here, because regressor we have already calculated just by giving that one. Now see, just to give you an idea as to the use of libraries. Now simply we have imported that library, and now we are writing this code to calculate all these things. Now this calculation is done, how it is being done, that of course we need not know and we don't know, but definitely by writing the code appropriately we are getting the results. So here we are going to get the result by printing it. So once we run it, you will see that there is some problem in this print regressor or something has been, oh sorry, yeah, this we have not run, so that is why. So you can see this we have got here linear regression, copy x true, fit intercept true, and job values normalize false. So then again we can run this, right, and then we can run this. So now we have got it. So now see, anything that you miss out or you don't do it properly, immediately you will get an error. So to retrieve the intercept, print a regressor. You got this. The intercept as 10.66185201 and print a regressor coefficient as 0.920339997. So this, of course, this result has got, we have got it. Now the result should be approximately 10.66 that we have got and 0.9203 respectively. So this result we have got. Now this shows, this means that for every 1 unit of change in the minimum temperature, the change in maximum temperature is about 0.92%. This is what we can conclude from there. And that is why, if you remember when we were talking about the inferences and descriptive statistics, etc., it is very important that we must know that what result will come and how we are going to interpret it. So here, that is how we can interpret it. So, like here it is mentioned that this means that for every 1 unit of change in the minimum temperature, the change in the maximum temperature is about 0.92%. Now we have trained our algorithm. It's time to make some predictions. Now we have to go for the forecasting. So we have to predict it. To do so, we will use our test data. Now we are going to do it on the test data because training has been done. Training we have done on that data set, that 80% that we have segregated. Now we are going to apply that our model on the test data, so that to find out whether it is correct, it is coming correctly or not. So it's time to make some predictions, and to do so we will use our test data and see how accurately our algorithm predicts the percentage score. To make predictions on the test data, execute the following script. Now this is ypred, because y test data is to be predicted. Regressor, of course, we have got. Predict x test is the data on which we are going to predict it. So that is why this kind of a code has been written, right? And here we are going to run it. So you will see that the ypred will be available here. Now again here, just to explain it further, now compare the actual output values for x test with the predicted values. Execute the following script. So again we can run this, and now we are going to actually calculate. So df is equal to pd data frame actual y test flatten. Y test is that because that we have already done. Predicted y predict that we have seen earlier. Ypred flatten, because flatten means that you have to smoothen it out, and then you are going to print that df. Df means that whatever value has come in, we are going to print it. So we can also visualize comparison result in a bar graph using the below script. Note, as the number of record is huge, for representation purpose I am taking only 25 records only. So this is how you can select only 25 top records. That is why it is taken as df1 is equal to df head only 25 record. df1 plot kind is only bar type. Fixed size is 16,12. Here grid, which is major, line style is dash, line width is 0.5 and color is green. The second one is minor, line width is colon and line width is 0.5, color is black. Now we are going to show the plot. So when we print the graph, you will see that you will get something like, oh wait, this doesn't matter. Oh, this also we have not done, sorry. So before that we have to run this. We have not run that. Now once we run it, you can see that actual and predicted will be available to you. So you can see that the difference between the two is not very much, but it is not something which is very accurate also. So 28.28, this is actual and this is the predicted one. This is again actual, predicted one, like that. They are quite close, right? And similarly for the bottom some rows. Now you can also visualize the comparison which we have seen. Again we can run that. Once we run that, then you can go for and see that This is the grid, whatever we have given here. Bars have been created, green and yellow color, and then this is the way you are going to get the bar chart with that data, right? So this is how you can go for it, and this is our actual versus predicted ones. This also you can say it's not very bad, but definitely not very good, because the differences are there. So, right? So this is the way you can see. This is actual one is the green one, and predicted one is the yellow one, right? Now, though our model is not very precise, the predicted percentages are close to the actual ones. So let's plot our straight line with the test data. Now we are going to, we are trying to print it again. So let's see. This of course nothing will happen. Here we are going to plot scatter x test. Now only with the x, the test data that we have taken, that is 20%, we are going to print a scatter graph again in the color gray, so that you can distinguish between the two. Then plot x test, y pred, color is equal to red, and line width is equal to 2, so that your line also becomes very clear. And then plot show. So once you run this, you will see that another plot will come like this. This is again a scatter plot with the test data, and you will see that this is the way the graph will get printed, right? So this is how you will get it, right? Now the next is the straight line that you are getting in the red in the above graph shows our algorithm is correct, because it is in the right direction as we expected. And the final step is to evaluate the performance of the algorithm. Now we have to also check whether our whatever algorithm that we have decided and without which we have written the code, whether that is also correct or not. So we have to evaluate that. So this step is particularly important to compare how well different algorithms perform on a particular data set. For regression algorithm, 3 evaluation metrics are commonly used. Now if you remember, we have imported the metrics also from scalar. So now the role of that matrix has come in here. So we can run this again like this. Nothing will happen here. Now we are going to have the mean absolute error is the mean of the absolute error of the value of the errors. Run it, nothing will happen. This then mean squared error, MSE, is the mean of the squared errors. Again nothing will happen. Then the next is root mean squared error, is the square root of the mean of the squared errors. Again nothing will happen, because these are all remarks. Then scikit-learn, sklearn library comes with a pre-built function that can be used to find out these variations for us, these values for us. Let's find the values of these metrics using our test data. Now test data is going to be taken into consideration so that we can find out this value. So again we can run. This is again for your explanation. We should receive output like this, put probably slightly different. Again we can run that also. And now the code. Now you can see the code is print mean absolute error, mean squared error, and print root mean squared error. Now matrix is being used. So matrix dot mean absolute error y test is the data, and y pred, the value that we got earlier. All those are being used here. Similarly here for the root mean squared error, y test, y pred, same data, y test, y pred. Again we are calculating the matrix mean squared error. So once we run it, you can see that you are going to get these 3 values. Mean absolute error is 3.199, mean squared error 17.63, root mean squared error is 4.19. We can see that the value of the root mean squared error is 4.19, which is more than 10%, right? We can see that, which is in front of us. And of the mean value of the percentage of all the temperature, that is 22.41. This means that our algorithm was not very accurate, but can still make reasonably good predictions. So this we can again run. Of course nothing will happen here. So we can see that in this manner we can calculate the linear regression. And that is how we have seen how the prediction can be done, how the other the errors part has been checked. All these things are possible. So this is how the linear regression exercise can be done. Thank you.